Hi, everyone. Thank you for joining us today. My name is Oded Grabowski. I'm Director of Product and Program in TriEye. Together with me today, Professor Riel Levy, co-founder and CTO in TriEye, one of the world's leader in nanophotonics and optoelectronic devices. Thanks for joining. We are going to take you through a use case analysis that we have recently done here in TriEye. We'll navigate the challenges of lost cargo detection. Let's set the stage first. We're going to base our analysis on a regulation, an existing regulation that was recently adjusted, updated. It was updated in a way that brings new challenge to the industry. The UN R157, which is known for detailing the requirements for automated driving, was extended to support a speed of up to 130 kilometers per hour. The regulation itself does not dictate the exact level of automation per the SAE definitions. However, we consider that as relevant feature already as part of the level 2 plus systems that already exist on the roads. This new regulation brings a new challenge to have a more advanced sensing capabilities, farther than what already exists by companies and already driving in cars. And this challenge brings a new requirement to have a fully reliable system with extended capabilities and scenarios. And when we talk about reliable, we mainly focus on confidence and repeatability of the system. Again, on the challenge, this transition from 60 kilometers per hour to 130, which is the edge speed for highway driving for automated vehicles. This was described in the regulation in a way that was calculating the distance that is needed to allow detection, to provide detection, to support certain speeds. This calculation is based on deceleration level and braking speed and distance. And as you can see in this table, which is a copy-paste from the regulation itself, to achieve a specified maximum speed of 130, we need to have a detection capability in a distance which is at least 150 meters. And this is what we're going to focus on today. How can we detect objects and what is needed to detect reliably to detect an object in 150 meters away. Moreover, the regulation also refers not only to the distance and speed, but to the environmental conditions that should be supported by the system. The ADAS system that are implemented in vehicles should be able not only to operate in severe conditions, but also to be able to identify those conditions and reduce the level of engagement of the system in operation, and also to notify the driver accordingly. Moving to safety enhancement that are derived from those basics requirements and challenges, there are a few definitions that come with it. So first would be a passable object. The requirement speaks about passable or not terminology, which means a passable object would be one that once identified by the system will allow the vehicle to continue driving continuously without any emergency or any action that is needed. However, when an object is classified as not passable, it means that an immediate action is needed for emergency brake or maneuver. So the vehicle could obviously avoid a collision, and that's the main goal. We wish to avoid any kind of collision, whether it's passenger car, cyclist, pedestrian. But mostly today we will focus on unknown objects, random objects that are blocking the road that could not be classified under a specific known object that already have a reference in the system. So that's a few definitions. Moving on to a few KPIs and what is needed for a system to be able to recognize and detect objects. Although this is This is a long discussion that is ongoing, but after analyzing this and talking with customers and in the industry, there are pretty generic dimensions that are agreed. Whether an object could be classified as passable, it is usually around 15 centimeters in height in the vertical direction and a width of 40 centimeters. And relatively to that, also a minimal number of pixels is required to enable classification for such an object. 6 pixels at least on the horizontal direction and 4 pixels on the vertical one. We will mostly discuss today on the vertical target as having 4 pixels. It's very minimal number of pixels that is actually the most critical aspect when you wish to drive over an object. And this is also referred to a ground clearance of a certain vehicle. So those dimensions refer to a generic passenger vehicle and could be a bit different for commercial or trucks. After defining the ground for the dimensions, the number of pixels, also the regulation and the industry look at the different conditions which derive to weather conditions, lighting conditions, and driving scenarios. So weather obviously refers to fog, rain, different humidity level, snow, etc. And some of them should be, when it's in a severe condition, the regulation allows some kind of a degradation, reduced performance for the system, but the system must be able to support those in general. As for lighting conditions, obviously light, twilight, and nighttime all should be supported as well. And different driving scenarios could be many other interferes from the environment. Either it could be an oncoming vehicle with headlights that is blinding, sun glare, tunnels moving in or out of a tunnel, etc., etc. All right, so now I'm going to pass to you, Uriel, to give a bit more deep dive into the different modalities that currently exist and have some comparison between them.
Thank you very much, Oded. Yeah, I will try to discuss a little bit the landscape and to try to explain the different modalities. We first start with the camera. As for the camera, it is a passive sensing modality, meaning that the signal is based on sunlight which is reflected by the object, or signal that is coming from the headlamps and reflected from the object. So the performance are heavily dependent on the ambient light conditions. Comparing that to a LiDAR, it's a different scenario because LiDAR is an active sensing modality. The signal is based on the laser light, which is reflected by the object. The detection is also based and relies on the sensor sensitivity, on the system design, and it actually provides accurate range and direction. If we are thinking about FMCW LiDARs, they also provide, on top of accurate range and direction, they provide also direct velocity information. Generally speaking, the performance are highly dependent on the illumination wavelengths. We used to separate between 2 major spectral regimes. One is the surrounding of 900 nanometer wavelengths, where we have limited detection capability, mostly due to the eye safety considerations, meaning that the power, the energy of the laser is limited due to eye safety, which in turn is limiting the signal that we can achieve. On the other hand, we have 1500 nanometer, the shortwave infrared or the telecom regime. This is eye-safe spectral regime. So in terms of signal, we can get much higher signal. However, on the other hand, it is expensive because there is no CMOS sensor which can accommodate to this wavelength regime. Thinking about imaging radar, it's active modality. It is based on RF illumination rather than standard light. It's RF. And again, reflected signals are highly dependent on the object materials and its ability to reflect or absorb. the RF frequencies. When we say RF frequencies, we typically discussing range somewhere between 20 gigahertz and 77 gigahertz. For example, metal objects are highly reflective, which is in general good. Sometimes it's actually too much because high reflection may saturate the scene. On the other hand, where we are talking about non-metallic objects, some of these are sometimes almost undetectable due to the very low reflectance. In general, we can say that the detection provides direction, range, and velocity. Then we come to SEDAR. SEDAR is the platform of TriEye, and it is based on active illumination in the SWIR regime. SEDAR stands for Spectrum Enhanced Detection and Ranging. It is again active modality. The signal is based on a laser, which is reflected by the object. It is based on an eye-safe SWIR illumination, and that's why we can have high power illumination, and obviously we can get much better signal. It operates at a specific SWIR wavelength where the SNR is optimized. So we have optimization of signal to noise ratio even at adverse weather condition. And the reflected signals are generally less dependent on environmental conditions and on the details of the scene. We are looking at three major key attributes. One would be resolution, the other one would be environmental condition, and the third would be perception. Let's now start to discuss each of these independently. So the first, of course, is resolution. And obviously, one may ask, why does resolution matter in lost cargo detection? And there are many reasons for that. First, it affects the detection capability and ultimately the reliability of the decision-making, whether we have detected or not detected a lost cargo object somewhere on the road. Then it affects the size estimate error. So we have a way to estimate the size of the object based on the image, and the lesser number of pixels, the higher the error in this size estimation. So that's a major issue. Now the contrast coming from the background is always challenging with low reflectivity objects. So in general, more pixels are needed to detect the object. So it's again a question of resolution. The better the resolution, the better our ability to differentiate contrast from the object. Then we have the issue of partial pixel coverage. We might see the image by, say, 4 pixels, or maybe by 4.5 pixels or 4.7 pixels. That's what I mean when I say partial pixel coverage. And this is an issue. Typically, when we have partial pixel coverage, we have lower signal, and therefore, there's less likelihood to provide detection. And finally, failure of single pixel may affect the whole process. And obviously, the more pixels we have, the less of an issue is the failure of a single pixel. We can look here down to see the difference between the case of 2 pixels versus 4 pixels. So you see that in the case of 2 pixels, the object is barely detectable. We basically say this is a no-go case. Whereas we have 4 pixels, we see the image better. We can really detect now the object, and this is the case where we define it as a go. Going into the detailed calculation, let's look at the scenario of a car driving at a speed of 130 kilometers per hour, where the distance between the car and the object is 150 meters, and the height of the object is about 15 centimeters. Now, if we do the calculation and we assume a minimum of 4 pixels in the vertical direction, we come to the conclusion that the minimum angular resolution that is needed is about 0.0125 degree per pixel. And this is actually the minimum requirement. Actually, if we think of the grid of the pixel, which is not fully aligned with the object, that could be even more severe. And that's why we are typically defining the needed angular resolution to be in the order of 0.01 degree per pixel. So now we are looking at the different modalities and we ask, can they provide this required angular resolution? We start with the camera, and the camera is the market standard, of course, and even if you take a market standard automotive camera, they are usually coming with high resolution, which definitely fulfill the task, assuming that the environmental conditions allow. So if we haven't sufficient environmental conditions and sufficient lighting, from resolution point of view, camera can do the job. Now we go to a LiDAR, and the current state of the art in the LiDAR, they are operating with angular resolution of about 0.1 degree. So 0.1 degree is good, but it's not good enough for this specific use case that we have just mentioned. There is an order of magnitude missing between the need and the current capability. If we look at an imager radar, this is even more problematic because the angular resolution of a typical imaging radar is somewhere in the range of 0.5 degree. So 0.5 degree per pixel, that's not enough. We need much better than that. Going to the SEDAR platform, we are talking about 2 megapixels, and this is why TriEye SEDAR can provide the 0.01 degree angular resolution, which is really needed for the lost cargo use case. So after discussing resolution, we move to the second key attribute, which is environmental conditions. Again, we have the 4 modalities, and according to R157, system provider or the OEMs, they must declare the supported ODD, and furthermore, the system shall be able to continuously monitor the environment and disable the ALKS feature where driving occurs outside of the defined ODD. So if we think of a camera, camera is by design the most vulnerable sensor when it comes to lighting conditions or to adverse weather conditions. Now, being a passive sensor, it is entirely dependent on external lighting. Cameras are limited in various conditions, including low light, blinding light, sun glare, sharp transitions in lighting conditions, and weather conditions, adverse weather conditions such as rain, fog, and dust. Moving to LiDAR. So LiDAR is definitely more immune to lighting conditions, to various driving scenarios, and to bad weather. However, it still has some vulnerabilities, still have some issues. So basically, I can say that LiDAR perception capabilities are often not sufficient to identify weather conditions with a reasonable level of confidence, which is crucial to determine whether it is operating within or outside the ODD. Moving to imaging radar, we all know that imager radar, like any other type of radar, are immune to lighting conditions, driving scenarios, and bad weather. This is because the wavelength which is being used is in the RF domain, frequencies in the few tens of gigahertz. They can be transmitted through the atmosphere without much of interference. This is why, in practice, these imaging radars can perform normally under adverse weather conditions. Finally, we talk about our SEDAR platform, and the SEDAR platform, if we compare it to a LiDAR, then the SEDAR offers significantly better performance in adverse weather condition, also immunity to different lighting conditions and driving scenarios. Same if we compare it to a camera. Basically, I can say that it is more resilient to these conditions compared to the competitors, and it has the capability to detect and declare the object very effectively as compared to LiDAR and camera. Can actually summarize what I've just said by this table. So we look at the 4 modalities on the left, and we look at 5 different criteria on the verticals, on the columns. So we can think of scenario of daytime, nighttime, HDR, light weather condition, and severe weather conditions. And as you can see, camera has lots of issues in these scenarios, especially at nighttime, at severe weather conditions, and even sometimes at light weather conditions that could be an issue. LiDAR perform better, daytime, nighttime it can perform fairly well, provides sort of mid-level, let's call it HDR, can really perform reasonably at light weather conditions, but it definitely has issues when we are talking about severe weather conditions. As for imaging radar, I've already mentioned it performs very well under severe environmental conditions, but so do our SEDAR platform, which perform very well at day, at night, under HDR, at light weather conditions, and even it performs fairly well at severe weather conditions. I think I will move on now to you to describe perception. Please, Odette.
Thank you, Ariel, for this deep overview of the different attributes. Moving on from these fundamental technical capabilities to perception. So perception is it's a critical step in the whole process, from having a sensed object on the road to the end of the process of decision making. And perception brings with it many aspects from the sensing stage. And for lost cargo use case, as we call it, it's very unique because unlike any other cases, other well-defined categories such as cars or pedestrian or different well-known shape and size objects, a lost cargo is by definition an unknown object. It could be anything that fell off a truck, stayed on the road after an accident, or any random object on the road that could not be classified by a pre-known or reference-known data within the system. And therefore, the challenge here is even farther than just having the capability to detect. So when we talk about lost cargo, detecting usually a very small and random object will be crucial for the safety, for the end safety of the drive, and that brings the challenge task to the AV or to the ADAS system. A few tasks by order that we see in this perception process would be first to detect that an object is there on the road blocking the way with a sufficient confidence of detection, and with that to measure the object range. How far is it from the vehicle at the very moment of detecting that it is there? After understanding that there is something on the road and how far it is, there is a fusion task to collect information from all the sensors within the sensing task at the moment, and try to solve conflicts between different data that is coming from different sensors, align different images and the region of area of interest between the different modalities, so that we can estimate the object size and later on feed the decision-making algorithms with a reliable outcome of object size, range of the object from the vehicle, and related confidence level, so that the decision-making algorithms can meet the true positive rate that is usually very, very highly strict required, and obviously to avoid any false alarm. We've tried to put in a diagram, a very simplified diagram, this whole process. So starting from having a lost cargo on the road up to the moment that there is a decision making of emergency brake or maneuver, we are focusing on a very specific of this very specific use case of lost cargo, and we are defining the capabilities, not defining, but analyzing the capabilities of different modalities to be able to support this process and bring to a reliable decision. So when we talk about the beginning of the process, there are two aspects in detection, which is to be able to see at long distance. And then, as Uriel mentioned, when it comes to resolution, it's not only enough to see that there is something there, you need to have enough pixels for reliable detection. So this is for the detection aspect of it. And then eventually to be able to estimate the size, since there is no reference for the very random object, there must be a reliable range estimation. And each one of the modalities that are listed here and compared during this session, each one of them has its own capabilities for detection and range estimation. And we will touch it in a minute, but it's important to understand that this is a very critical step in the whole sensing and perception process, because eventually a decision whether the object is passable or not, meaning the vehicle could drive over it and ignore it, or not, meaning to have an emergency action, a brake or a maneuver. For that, there must be a reliable size estimation of the object. And that would only be possible with a calculation that is based on the detection and the range estimation. So when we see the different modalities and also the SEDAR, so we see that for detection, for example, the camera could detect very well at daytime, at very nice weather, but is very limited when it comes to nighttime and also severe conditions. When it comes to range estimation, camera is highly limited, mainly when it comes to a random object. For imaging radar, detection is highly limited due to low resolution, and range estimation is solid, is pretty accurate. Again, in the LiDAR, also we have a reliable range estimation in variety of conditions. However, to allow detection in long distance, this is again limited due to resolution and other interference that might not bring a good enough image. SEDAR, on the other hand, the platform that we are developing here in TriEye, it's a given, the output of the SEDAR is a given synchronized 2D and 3D map, meaning there is not only a high quality image, just like a camera, but also a synced 3D map with a range estimation for each pixel that is in the image. There is also a range level. That brings a very easy option to calculate and to estimate the size of the detected object without any fusion needed. And therefore, when we look on the process in high level, and we try to understand how can the sensor set of a vehicle get to a reliable decision in such a corner cases, such a challenging cases of having a lost cargo in a very high distance of 150 meters at least. This is highly dependent on a limited fusion of modalities, which bring a lot of challenges within this fusion. For example, there must be a perfect alignment between the different modalities which are bringing a different type of data. For example, a point cloud of LiDAR is different than an image in a camera, and aligning them into a reliable fusion is a limited task. And obviously, when it comes to a decision that should be taken in an immediate manner. So to summarize that, the whole perception process is, after all, relied on the possibility to bring a reliable size estimation. And we consider the SEDAR to have all-in-one on this aspect, meaning not only to have high operational level in variety of conditions, but also to bring the exact data that is needed, range and detection in high resolution. Okay, yeah, so we discussed a lot of topics today, and try to summarize it up into a one comparison table here between the modalities. So when it comes to resolution, as discussed, and also different environment conditions, starting from lighting and drive scenarios or different weather conditions, it all bring the capability to have a good enough perception at the end of the process. And we see that SEDAR is standing out when you combine the whole picture. And therefore, when it comes to the lost cargo use case, we see the SEDAR as a revolutionary platform to support this upcoming regulation and challenges in the market. A few examples from our demonstration systems, our system that we already build and test. So in this case, you can see this is a scenario of a pedestrian crossing behind the vehicle, oncoming vehicle that is with the headlights lighting towards the ego vehicle. And you can see on the right-hand side of the slide, you can see the visible camera, regular camera, fully glared, cannot see by any chance the pedestrian crossing. And it's a very important step in time, because if the vehicle is driving in 130 kilometers per hour, so there is only immediate opportunity to take the emergency action and to avoid a potential accident. And you can see here that when you look at the SEDAR output, the image on the left side and the range map in the center, this brings a very good picture and information for the system to rely on when taking such an emergency action. Focusing again on small objects, as we discussed the lost cargo today. So this example again, in a distance of 150 meters, the ego vehicle is equipped with the SEDAR platform and sensing very small objects in a distance where the smallest one of them is in a size of 15 by 15 centimeters, the very left object that you can see. And again, comparing to a visible camera, it wouldn't be able to detect this object at nighttime or in dark areas. And therefore, when the decision might be taken, it wouldn't be enough to rely on camera here. And also, as mentioned before by Professor Levy about resolution, definitely you have to have enough, good enough resolution, in this case, at least 0.01 to be able to, degrees per pixel, to be able to detect such a small object in this distance. To summarize up the discussion, again, thank you for joining us to this session, but to a few takeouts. So when we go back again to discuss the regulation, the R157, it's basically all about the system should be able to detect a lost cargo at a distance of 150 meters, to be able to classify this object as possible or not. So either an emergency action should be taken or not. It should ensure that the detection is resilient to environmental conditions and operational in a variety of scenarios, and guarantee that the classification is robust, it's reliable, consistent, of course. After taking all these into account, we learned that the SEDAR platform is the only sensor today that can support this and allow the ADAS system to meet those conditions, those very highly challenging requirements of the regulation to meet and to be able to support the lost cargo use case. So that's our takeout. Thank you again for listening and joining us today. Please feel free to reach us out, to send us an email or visit our website and contact us to further learn on this topic of lost cargo detection, and of course to discuss the TriEye's solution to the automotive industry. Thanks again, and see you next time.
Thank you very much.
Thank you.